Okay, so I'm just going to do some examples for probability density functions, or PDFs. So this first example, the function is defined as f of x is x cubed on 60 for the domain from 2 to 4, and 0 for all other values of x. Show that it is a continuous probability distribution. Okay, so it's a cubic function, so it is continuous. We know that already. There's no limited domain for x cubed over 60. So to show that it's a probability distribution, we need to show that the area under the curve equals 1. Okay, so we find the area under the curve from 2 to 4 of x cubed on 60 with respect to x. Okay, so we integrate that, so increase the power by 1, divide by the new power. Dividing, of course, is the same as dividing by 4 is the same as multiplying by 1 over 4, so 4 in the denominator, and that's from 2 to 4. Okay, so let's plug in those values. So 4 to the power of 4 times 60 is 240, minus 2 to the power of 4 on 240, and that does equal 1 if you put that in your calculator. So it is a continuous probability distribution. Okay, so in part B, we're actually going to calculate some probabilities using this PDF. So the first one is the probability that x is less than or equal to 3. Now, the important thing here is to realize that our domain starts at 2. So that literally just means that we're finding the area under the curve between 2 and 3 of the same function. So x cubed on 60 with respect to x. We've already integrated that above. We know that that was x to the power of 4 on 240. But this time it goes from 2 to 3. So it's exactly the same thing. You're plugging in 3 and 2. So 3 to the power of 4 on 240 minus 2 to the power of 4 on 240. And that is equal to, I believe, 200, oh, is that right? 221 over, no, that's not the correct answer, sorry. That was my answer for another problem. Let me just quickly throw that in my calculator. So 3 to the power of 4 minus 2 to the power of 4 over 240. That is equal to 13 over 48. And in our second problem, we want to find the probability that it's between 3 and 3.5. Exactly the same thing. So this time from 3 to 3.5 of x cubed on 60 dx, which is x to the 4 on 240, from 3 to 3.5. Yeah, you could probably fast forward through this part of the video if you wanted to. It'll just take me a moment. You might ask yourself, do we need to do this every single time? That answer is going to come in a later exercise. For now, yeah, it's good to do it just for practice. Okay. In number 2, we have to show that this curve is a PDF. Now, just like in part 1a, what we're doing is showing that the area under the curve makes 1. So if this is a third, then each of these are a ninth. A third divided by 3 is a ninth. So let's just split it into a triangle plus a rectangle. So the area is, let's go the rectangle first, so the height of that is 1 on 9. I'll just put 1 on 9 there, times 6, plus the triangle, so half times the base, so the base is 3, times the height. So each of these is 1/9, so that would be 2/9. Put that all in your calculator, and yes, it equals 1, so yes, it is a PDF. And just one more example, number 3. Find the value of a such that y equals ax squared is a PDF on the domain from 2 to 5. So this is exactly the same. The integral from 2 to 5 of ax squared with respect to x has to equal 1. That's what we need to solve. So let's integrate. Now you can actually factor the a out the front if you want to. So as if the a was in front of the integral sign. Any constant can just go in front of the integral sign without a problem. So it's x cubed on 3, should be square brackets, from 2 to 5 is equal to 1 So a times plug in the 5, so 5 cubed on 3 minus plug in the 2, 2 cubed on 3 equals 1. So 5 cubed on 3 minus 2 cubed on 3 is 121 on 3. So a times 121 on 3 equals 1. So let's multiply by 3. Let's divide by 121. A is equal to 3 on 121.